Hi, good morning everyone. This side Amit Kumar and physics faculty, and today we are going to deal with a topic called work energy theorem. So this is another way to approach the mechanics problem, the energy approach. So today I am going to discuss about the work kinetic energy theorem, which incorporates the idea of kinematics as well as dynamics. So we will start with the previous situation that a body of mass m is placed on a frictionless surface. A body of mass m is placed on a frictionless surface and it is pulled by a force F which makes an angle theta with the horizontal. This is not a new situation. This is the old situation in which a body is sitting on a frictionless table and the body is pulled by the force F making an angle theta with the horizontal. The initial velocity of the body is u, and after time t the velocity of the body becomes v. Okay, and during time for which the force F is equal to t and the body displaces through a distance h. Okay, so we will use the kinematic situation as well as the dynamic situation, and as we can see here, there is a component of force F cos theta which acts horizontally and a component of force F sin theta which is acting in the vertical direction, the weight of the body mg which acts downward, and this is a normal component of force. This picture denotes the free body diagram of the body in which the body is moved along the horizontal direction. That's why the net force acting on the body is in the horizontal direction. There is no motion incorporated in the vertical direction, hence n plus f sin theta is equal to the mg. The only component of force which acts along the horizontal direction is f cos theta and which produces the acceleration in the body. Here in this situation we can see the force acting on the body is constant and the inclination with the horizontal is also constant, so that the f cos theta which is acting along the direction of displacement is also constant. So from the Newton's second law, the net force causes the acceleration. So from the Newton's law we can write f cos theta is equal to ma. Means the f cos theta which is acting on the body produces the acceleration, hence the acceleration of the body is f cos theta by m. Okay, this is our first equation. As the body is acted by a constant force and the mass of the body is also constant and value of the cosine of the angle is also constant, the acceleration produced in the body is also constant. Okay, so if a body is moving with the constant acceleration, we can use the kinematical equation, and we will use here the v square using the kinematical equation v square is equal to u square plus 2as. This is our equation number 2. So we will use these two equations to introduce the concept of energy, and we, after deducting the expression, we name that form of energy as the kinetic energy of the body. We will also elaborate the concept of the water. Okay, now using equation 1 and 2 and putting the value of acceleration in equation number 2, putting the value of acceleration in equation number 2. So from equation number 1, from equation 1, A equals to F cos theta divided by M, and from equation number 2, V square is equal to U square plus 2AS. So putting the value of acceleration in the equation number 2, we can write V square is equal to U square plus 2 into F cos theta divided by M into S. After simplifying all this equation, we get an equation half mv square minus half mu square equals to F cos theta into S. Okay, this is the new interpretation of the equation. Here the LHS stands. We can see the physical quantity appeared in the LHS. 1 by 2 is constant, m denotes the mass of the body, and v denotes the final velocity. In the same way, in this equation, m denotes the mass of the body, and u denotes the initial velocity. The expression, the physical expression in the LHS is what? 1 by 2, product of 1 by 2 mass of the body into velocity of the body k square. And in the RHS, there is F cos theta. This is the component of net force which is acting along the direction of displacement and displacement. We call the expression half into mass into velocity k square as kinetic energy. We name this expression half mass of the body into velocity ka body k square as kinetic energy. Hence, the kinetic energy of a body, the energy possessed by the body, is the virtue of its motion. So LHS denotes, the first term in the LHS denotes the final kinetic energy, and this is the initial kinetic energy, and we name the quantity in the RHS. This denotes the component of the force acting along the direction of displacement. We call it the work done. So we can write half mu square as the initial final kinetic energy, half mu square as initial kinetic energy is equal to work done. LHS denotes the change in kinetic energy of the body is equal to work done. Okay. So this expression shows that the work done by the net force is the change in kinetic energy of the body, and if a work is done on a body, that is interpreted only in terms of the change in kinetic energy of the body, and this is a very profound rule in the energy analysis of the mechanics problem, that the work done by the net force is equal to change in kinetic energy of the body. For now, this video is for the demo purpose. For now, I have concluded my argument, and this topic is concluded. Thank you very much. Thank you.